Hello everyone. Today we'll revisit the Atwood machine. That's the pulley system which we encountered in Unit 2 when talking about forces. Today we'll use energy conservation to find the final velocity of the system. Let's get right to it. A light inextensible cord passes over a light frictionless pulley with a radius of 5.6 centimeters. It has a 22 kilogram mass on the left and a 5.1 kilogram mass on the right, both hanging freely. Initially, their center of masses are a vertical distance 4.5 meters apart. The acceleration of gravity is 9.8 meters per second squared. If the system starts out from rest, how fast is the 22 kilogram mass moving when it hits the ground? Ignore air drag. Okay, so in Unit 2, when talking about forces, we had to draw a free body diagram, and then we did some algebra to find the acceleration. For this one, we'll use energy conservation. There's another method, and I will record a different video for that one. Just pick the one that you like best. For this one, we'll use energy conservation. And we had two equations for energy conservation. Well, actually it was one, but then we simplified and came up with the second one. Let me write the longer one, okay? So before we write down the given, I want to remind you about the equation for energy conservation. And it said, let me use purple, kinetic energy initial plus potential energy initial plus the work done by non-conservative forces plus other energies initial is equal to kinetic energy final plus potential energy final plus other energies final. In this case, we're not considering tension because the cord is inextensible, and then we're not considering internal energy, anything like that, so other energy is out. Also, we're not dealing with any non-conservative forces because we are ignoring air drag. Therefore, our equation simplifies rather nicely to kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. There you go. Okay, that is the equation we're going to use to solve this problem. Let's write down the given. I'm going to use blue. So given. Let's try that again. Okay. Let's highlight things that we know are important. So of course that the cord is inextensible. It is very important because that tells you the problem is simple. And then the pulley is frictionless, so we're not considering friction. The radius is not important in this case. I don't know what they put it there. I don't want to say it just to throw you off, maybe not. But it is not important. At least not for now. We know that we have a 22 kilogram mass, 5.1 kilogram mass. We have this one's on the left and this one's on the right. And there's a vertical distance between the center of masses. That is very important. And, well, we know the acceleration of gravity, as usual, is 9.8 meters per second squared. Also, the system starting out from rest, that is very, very important. And we want to know how fast. That means velocity. And I know that it says 22 kilogram mass. It kind of suggests that this mass, 22 kilogram, would have a different velocity than this one. But it is important for us to know or to see that the motion is based on this one, but as the 22 kilogram mass moves down, the 5.1 mass is going to move up. Okay? So the velocity of mass 1 final will be the same as the velocity initial from mass 1 because it is a system and they are connected by the same cord. Okay? So now let's write down the given. So we have I'm going to call this mass 1. I'm going to call this one mass 2. So mass 1 is 22 kilograms. Mass 2 is 5.1 kilograms. That's a weird K, but it's okay. And then we have a distance, okay, of 4.5 meters. In this case, I'm going to call this distance initial height. And this is initial height for mass 1. Okay, initial height for mass 1. So I'm going to call it HIM1. I know that's a lot of subscript, but that is what it is, right? Initial height for mass 1 is 4.5 meters. And then we know acceleration of gravity, which is 9.8 meters per second squared. And we want to know how fast is the system moving. I know it says 22 kilograms, but it'll be the same for both, okay? Whatever speed this one has at the end, this one will have too. So velocity final, we're trying to find. Now, let's write down the implicit given. Well, the system starting out from rest. So that means the initial velocity of the system is 0 meters per second. Because the 22 kilograms is going to start from rest, and so is the 5.1 kilogram mass. Okay, and then one more thing. We can't know the initial height for mass 2, right? Because this one's ground level, we're assuming that. So we are assuming that at this point, it would change. So we're assuming that this height over here, this represents the height equals 0 meters. That means the initial height for mass 2 is 0 meters. That's important, you'll see why later on. Okay. So there we have all the given, both implicit and implicit. We found the 0 quantities. Don't forget that I told you when you are working with energy conservation, at least one has to be 0. In this case, we have 2 of them zeros. That is very good. So now, let's write down the equation. Kinetic energy, initial plus potential energy, initial is equal to kinetic energy final plus potential energy final. What makes this problem a little complicated or complex is we have 2 masses. So our system has 2 masses, which means 2 masses are going to contribute to the kinetic energy. Same thing with the potential, and same case for final kinetic and final potential energies. That means there will be a kinetic energy initial for mass 1, a kinetic energy initial for mass 2. Same thing with the potentials, okay? So let's write down the kinetic energy initial for the system. So that means 1/2 mass 1 velocity initial squared plus mass 2. Okay, let's fix that. 1/2. There you go. Plus 1/2 mass 2 velocity initial squared. These 2 equations are the kinetic energy initial of this system because this is mass 2 masses. You have to do the same thing with the potential energy, gravitational potential, plus M1 GH initial. And one thing we have to, you know what, never mind, I'll say that later, okay? Plus M2 GH initial is equal to 1/2 mass 1 velocity final squared plus 1/2 mass 2 velocity final squared. Velocities don't have a subscript, like they don't have a 1 or 2 because the velocities are the same. Plus m2, sorry, it was m1, right? M1 goes first. GH final plus m2 GH final. Okay, there's a reason why I am not adding height initial mass 1, height initial mass 2, and let me tell you why, okay? That's a long equation, right? So if you think about it, the initial height for mass 1 is 4.5, but that's equal to the final height of mass 2, because when this one moves down 4.5 centimeters, this one will be up 4.5 centimeters. So that means height initial mass 1 equals height final mass 2. And then height final mass 1 equals height initial mass 2. Because the final height for mass 1 will be 0, right? When it gets to the 4.5 level here at 0 height. And this one is going to move up by the same amount. So when this one is at 4.5, this one is at 0. When mass 1 is at 4.5, this one is at 0. Okay? Hopefully that made sense. And let's cancel whatever we can. So the initial velocity is 0, so that means this one cancels, this one cancels. Well, the initial height for mass 2 is 0, so the potential energy initial in this case is 0. When mass 1 gets to the 0 height level, well, the potential energy is going to be 0. So there you go. And that's all we can cancel, I believe. Yes. There you go. Yeah. Okay. Let's rewrite our equation. So now it reads M1 GHI is equal to 1/2 M1 V final squared plus 1/2 M2 V final squared plus M2 GH final. We said that the initial height for mass 1 is going to be the final height for mass 2, and those are the ones we have left. So instead of having H initial, H final, I am simply going to call this one H, because it is the same for both. Okay? So then let's make that change. M1GH is equal to 1/2 M1 B final squared plus 1/2 M2 B final squared plus M2 GH. Let me fix that squared. Okay. And let me just remind you that the reason why this is simply height is because of this relationship. And we have to solve for velocity final, right? So I'm going to move this one, M2GH, to the left. My equation reads M1GH minus M2GH is equal to 1/2 M1 V final squared plus 1/2 M2 whoops, m2 v final squared. Now we can factor out the velocity squared in the 1/2, right, because that's repeated. So I'm going to factor out the 1/2 v final squared. And then on this side, I'm going to factor out the gh. So my equation reads gh m1 minus m2 is equal to 1/2 v final squared, whoops, v final squared m1 plus m2. Now to solve for velocity final, I'm going to get rid of this 1/2. And it's important that you don't get rid of this you don't get rid of this 1/2 until this point, because although I could have done it here, a lot of students think that when they cancel this 1/2 on the right side, they don't have to do anything on the left side. You do, or sometimes they do cancel the 1/2 on the right side, and they only change something on this term. But don't forget that if you cancel the 1/2 on one side, this side has two equations, and so does this side. That means both equations get affected. Since we factor out the h and made the left side only one equation, same thing on the right side, it's a little easier to see what happens with this 1/2. So we're going to cancel this 1/2. We multiply by the reciprocal, which is in this case 2 over 1, or just 2. So there you go. So now we have 2gh m1 minus m2 is equal to v final squared m1 plus m2. So now we divide by the sum of the masses, that is m1 plus m2. There you go. Don't forget, whatever we do to one side, we have to do to the other. And now, I think you guys know, right? To get rid of this square root, of this square, we take the square root. So I'm just going to write the final equation. But what I'm doing is I'm taking the square root on both sides. So I will add the square root at the end. Okay, at the end. So let's copy. There you go. Let's move this one. And let's add the square root. There you go. So that should give me my velocity. 2gh, the square root of 2gh times the difference of the masses divided by the sum of the masses. Let's go for decimals. So, you know what? Before using decimals, I'm going to substitute numbers. So that'll be final velocity is equal to 2 times 9.8 meters per second squared times mass 1, it was 22 kilograms, minus 5.1 kilograms. And that's going to be divided by the sum of the masses, which is 22 kilograms plus 5.1 kilograms. And then we take the square root. Now let's use decimals. Square root of 2, 9.8, 22 minus 5.1 divided by 22 plus 5.1. I forgot the height on this one. Let's fix that. Let's fix that real quick. I forgot the height over here. So I'm going to move this one. The height was 4.5 meters. That was my mistake. Good thing we caught it. and 4.5. There you go. So now we have it. Wait, I think, did I make a mistake on decimals? Yes, I have 4. There you go. There you go, much better. So here's our answer. I'm going to round to 2 decimals, so 7.42. 7.42 is the final speed of the system. So let's write that down. Final velocity is 7.42 meters per second. That is it, guys.